Yeah, hello and welcome to the 8th lecture in the course Programming and Data Structures. The topic for today is two techniques called hashing and binary search trees. Similar as we could implement a list using two different techniques. We were using arrays and we were using linked list. Today we'll take a look at another data structure called a set, and we will present two approaches to how to implement them. One is called hashing and the other one is called binary search tree. So there are two implementation techniques. I will start by saying a few words about Java collection classes. This is a name of the data structures in Java. So when your people are talking about the Java collection classes, they are talking about the available data structures in Java. We have seen a number of the so-called sequential data structures. The simplest one, but today, the topic for today will be to take a look at the sets, the set implementation that are available in the Java library. We will also take a look at how to implement hashing and also binary search trees. We spend a lot of lectures here studying data structures, and I think it is an important topic. First of all, as a programmer, you are constantly using different data structures. You need to collect data in some way, and selecting correct data structure is important from performance point of view. Also, I look at this data structure as examples of common techniques. For example, hashing is not only used in sets, they are the base for all databases. Databases are filled with hashing in different ways. And binary search trees, well, trees is a general data structure in Java, and it's also frequently used. So we will focus on set implementation, but remember that the techniques we are using today, hashing and binary search trees, are more general. They are used in different applications. As usual, when you're a programmer and you need a data structure, you should ask yourself two questions. What are the required properties of the data structure? Based on this decision, you say that I would like a list, a set, a map, or a stack. You decide what type of data structure. Then the second question is, which is the most frequently used operation? Then you decide what type of implementation to use. For example, an array-based or a linked if it comes to a list. So, I always recommend students to ask these two questions when you're selecting what data structure to use. This is a hierarchy of some of the collection classes that are available in Java. They have a topmost interface here called collection. This interface contains methods like add, remove, contains, is empty, and things like general questions that can be asked to any data structure. Then they have divided it into three different categories: the list, the queue, and the set. This will be the topic for today. And then they have a help class called abstract list that are used to implement three different versions of a list down here. Very similar to the first exercise in assignment 2. Then I was giving you an abstract collection class and you were asked to implement a list and a queue. They have such classes, abstract list and abstract queue, in the Java library, and they are using these classes to implement other concrete classes. But let's skip ahead to the set interface. What is a set? What is the difference between a set and a list? Set have no position. You cannot add an element at a certain position and remove it at a certain position. And also, if you try to add an element, it has a slightly different semantics here. Add t if not already added. Returns true if added. If you try to add the same element a second time, it will be ignored. So it can only contain, it will not contain any duplicate elements. And it has no position. That means we have no methods called remove at a certain position. You can remove an element, you can ask if it contains, but you cannot add it at a certain position. Consider it as a box. You're just adding things to it. It doesn't contain any position and it doesn't contain any duplicate elements. When are you using sets? Well, Want to make sure that the collection never contains two identical elements. For example, registered students on a course. If I want to make sure that we cannot register the same student twice, I would use a data structure which is a set. And as you will do in the assignment, count something. If I would like to count words in a given text, I just pick out the words and add them to the set. If I try to add the same set, same word 2 times, it will be ignored. So it will count the number of different words in a text just by adding them to a data structure. We also expect speedy lookup. By lookup, I mean add, contain, and remove. You will see that we can do it much faster in a set than in a list, for example. What is the time complexity of these 3 operations on a list? What? Linear, and it was called ordo n. The lookup time is proportional to the current size of the list that we are looking up. The drawback with using sets is that they have no position. That means you cannot get an element at a certain position, and you cannot remove an element at certain position. So methods that you're used to use on a list that are based on a position, they are no longer available in a set. They have 2 sets available in Java. One is called Java util hash set. The other one is called Java util tree set. The one with named hash set is based on hash string, and of course tree set is based on binary search trees. Here I have a simple example. I'm creating a new hash set that can contain strings, and I'm adding 4 names here. I ask it, what is your size? It will say size is 4. Then I add a number of duplicates. I add Jonas, Jens, and Jesper 1 more time. I'm asking it, what is your size? And it will still say 4. It is ignoring the second attempt of adding a new element to it. You can, of course, ask, do you contain Jesper, do you contain Maria, and remove Jesper, but no mentioning of position. The elements have no given position in a set. Do you understand how it works? Or how to use it roughly? Good. So set in Java, it is not a mathematical set. A mathematical set we are associating with operations like union and intersection and things like this. Sets in Java is not the same. Collection with no duplicate elements, and also I would like to add, we expect lookup to be very fast in sets. A very simple implementation of a set could look something like this. I use an array list as my backup structure. This is where I store my data. And the add method, where we are adding an object, I simply start by checking, do we have this element already? And only in the case we are not having this element already, then I'm adding it. So I start by checking, is it available? And if it's not available, then I add it. And then contains, many of the things will be the same. This is a very simple implementation of a set. It would do the job, but it would have a time complexity of add, remove, and contains would be ordo n. That means each time we have to search through the entire list to make sure whether we have the element or not. We can do it much faster. I will present 2 different techniques, and I will also talk a bit about the available classes. Java util hash set are using a hash table. That means they can do add, contain, and remove in constant time. If properly used, we don't have to search through it. We can, in a few computations, decide whether we have this element or not in a fixed time. The tree set are slightly slower than the hash set. They are working in logarithmic time, but still much faster than a list. The drawback with using a hash set, as you will see, is that they are no element ordering. You are adding the element in a certain order. If you ask for the iterator or iterating over the hash set, they will come out in any random order. The tree set is fast basically because they are keeping the elements sorted in a sense. So if you're adding a number of integers to a tree set and then you're iterating over them, they will actually come out in ordered fashion, the lowest first. And I will say later on a few words about something called a linked hash set. It's the third set implementation available in Java. This is a combination of a hash set and a linked list. But these two are the most important ones. Hashing. Yeah, I will show 3 slides where I will try to explain hashing to you, and I think it is important that you raise your hand and say, I don't understand, if you don't understand. Over here we have an array of linked lists. Think of it, each element here is called a bucket, but it is an array of linked lists. And we are saying that each linked list here with a position and a list is called a bucket. But think of it as an array of linked lists. Okay, I'm about to add a new element to the hash table. I start by associating this element with a certain integer. I must convert whatever it is into an integer. Then I apply the hash function. Hash function takes this integer and decides in which bucket to place it. Then I'm going through the list, and if I can find it in the list, then I'm not adding it. If I cannot find it, I add it to the list. So 3 steps. Associate each input element with an integer, decide which bucket to use, and then go through the list and insert it or not insert it. 3 steps to decide whether we already have it or we should add it or not. Assume we have a table with, say, 64 buckets. That means 64 linked lists. Assume that we compute the hash value for a string by summing up the ASCII codes for each character. That is our hash computation. We are associating each string with an integer, and we do it in this way. And we use a simple modulus operator as our hashing function, deciding which bucket to use. So this step we do by summing up all the ASCII codes, the sum of all ASCII codes in the input string. This step, deciding where to go, we simply do it by modulus for the size of this array. So if I would like to add the word hello, I would say that the hash value is 500. I have added all the ASCII codes here, and I will insert it into bucket 52, since 500 modulo 64 is 52. So let's go back here, or let's go back here. Assume I would like to add the word hello. I will compute the hash value 500. I will do the modulus, and I will go to bucket number 52. I will traverse the list and see if it's there, and if it's not there, I will add it to the list. Yeah? Adding Jonas, hash value 507, it will be bucket 59. Insert Jonas in bucket 59 if not already added. For each string I'm adding, we will do 3 computations. Compute hash value, compute bucket, and traverse the list. Assume now that all elements are evenly distributed across all buckets. That means our hash function is fair in the sense that it distributes all the elements across all buckets evenly. Also assume that the number of elements is roughly the same as the number of buckets. What will be the average length of the list in that case? What? Average length of the linked list in this case? 1. That means in constant time we will traverse the list. So we are doing 3 things. We are doing a computation, we are doing a modulus, and we are going through a list of size 1. Each of them have a very limited set of computation, independent of what element we are adding, it will take the same time. In constant time, we will add and remove and check if it is contained. So this is the reason why add, contain, and remove executes in a fixed number of steps. That means we are saying in constant time. If we have 1 million elements in a bucket of size 1 billion, it doesn't matter from 1,000. The work will be the same and the time will be the same to look it up. Did you get the idea? Important. We must discover when two duplicate elements are added. How should I... What parts over here must... If I'm adding two elements that are considered to be the same, what parts must work in this case? Similar means they must be associated with the same integer. If they are not associated with the same integer, they will end up in different buckets. And also, when we are traversing the list here, we must be able to see that these two are similar or not. So in Java, when you want to decide whether two elements are similar according to hashing, they should provide the same hash code, and the equals method should give true. Yeah. So all objects in Java is actually prepared for hashing. I've told you earlier on that they are all inheriting methods from the object class. So every class in Java is inheriting from the object class, and the object class defines two methods, equals and also hash code. So if you would like to have a student class or whatever class you would like to have, and you would like to use hashing, then you must override these two methods, because these two are used by the hash set. This one is used to associate the input element with an integer. This one is used when we are traversing the linked list to see if they are equal. So if you want to have a student class that works with hashing, you must override these two methods to indicate when do you consider two students to be identical. So hash code is used to associate each element with a hash value, and equals identify identical elements in the linked list. So similar objects. If you would like to add something to the hash set, and you would like to make sure that we don't have any duplicate elements, we are saying that two objects can be considered as similar if they have the same hash code and they have the same equals. So for example here, I have a class student. I associate each student with a name and a Swedish ID number, like this. Then I'm overriding the equals method. I'm saying that two students are equals if they have identical ID number. We are using the ID number as a key here. And also hash code, I'm saying that I would like to associate each student with an integer. It's the hash code method. I'm simply computing the sum of all the ASCII numbers here. I'm starting by saying that the hash code is 0. Then I am iterating over the ID number, pick out one character at a time, convert the character to an ASCII number, and add it to HC. So I am using here the sum of the ASCII codes for the ID number string as my definition of a hash code. Two students having the same ID number will be considered as equal in this case. Did you understand how it works? If you have done this, you have your student, you are overriding this method with your own definition of when two students are equal, and you provide them with a hash code, then you can start to use the hash set class in Java. You can start adding students to your hash set, and it will identify if you're adding a duplicate student. That means a student with the same ID number. Questions? This is my implementation of a hash set. I will show I have an interface called the string set. It is a set of strings, and I provide my own implementation, a hash-based implementation. This is the fields in my hash set. I am keeping track of the current size, and I have my array of my buckets. And each bucket is a linked list. And the linked list is simply this one that we recognize from the linked list implementation. So I have to start with an array of node. And I'm keeping track of the current size of added element. This one, initially in this example here, it just contains 8 different array lists, linked lists. Yeah, do you understand the setup? Okay, I would like to add a new string to this string set. I call the method getBucketNumber. The getBucketNumber down here, it takes the input string. It asks the string for its hash code. The string class already comes with its own hash code definition. So I'm just asking the string, give me your hash code, and then I would just like to make sure that it's non-negative. This method might give you negative numbers. So I'm just look, if it's less than 0, then I switch sign of it here, and then I'm using the very simple hash function where I just take modulus bucket length. Whatever string I'm adding here, it will give me a number between 0 and 8 in this case. Do you agree? So this is the first part. I identified in which bucket to insert it. Then I'm asking the bucket array, give me the linked list in this position. As long as the first node, as long as the first node is not null, I'm check is the node equals to this string. If that is the case, we have already found it. It's a duplicate element. Otherwise, we traverse to the next node. And if we are repeating this until node equals null, that means we have reached the end of the list. That means we cannot find this particular string in this particular array, in this particular linked list. Then I'm creating a new node and I'm attaching it to the bucket like this. Yeah. A very simple implementation of a hash set. Get the bucket number. Here I'm reusing this one to get in which bucket to insert it, and then pick out the linked list associated with this position, and then traverse the linked list and add it to the end if it's not already there. Yeah. Assuming that the average length here of the linked list is 1, this is done in no time. We have a fixed set of computations to decide whether it's in the list or not, in the set or not. Rehash. We are adding it and we are increasing the size. If the size is equal to the bucket length, I said that in order to get this nice property that we can look it up in a constant fixed number of steps, the average length of the linked list should be 1. The name of the number of added elements should be the same as the bucket size. So if I reach the bucket size, the size is equal to the bucket length, I'm calling the rehash method. And the rehash method just creates a new bucket which is twice as long, and it moves all elements from the previous one to the new one. So it's called the rehashing of it. So in the same way as with an array length, we start with an initial size. You should not use 8. You should use a somewhat larger number than 8 as your starting position. And we add elements, and when we have added 8 elements, we let it grow, and we construct a new hash table, and we continue with this one. This one is very fast. No matter whether you have 10 elements, 100 elements, or 1 million elements, it's 3 operations to check whether we have the element or not. What is, if you're implementing this, what can go wrong?
Like I tried it, but it doesn't feel feels always like 80% maximum.
Yeah.
So there's 20% like empty.
Crucial for its performance is that we have an even distribution of elements over here. For example, if I have a very simple hash function that always gives this, the number 1, then we will have all elements in one list here, and it will be a linked list, so it's no advantage. We must try to come up with one way of creating a large variety of different integers here, and we must make sure that they are distributed across entire buckets. So you have something like a student, and you would like to associate with a hash number. You must come up with something that is not, you cannot just take the first 2 digits in the ID number, because then it will only be a small variety of possible hash functions, and we will not use the entire this one. So to get an even distribution across the buckets is crucial for its for speed. And also, of course, make sure that we are increasing the size of this array when the number of added elements starts to get close to the array. It is crucial that the average length is about 1 for the linked lists. Otherwise, we will have to search through the linked list, and we lose the speed of it. Did you get the idea? You will be asked to implement a hash set in the 3rd assignment. It's not much. Basically, these 2 slides here is pointing out what you need to do. You must, when you add something, you will add an element called a word to your hash set, but you must associate this word with a specific bucket number, and then just look through the buckets like this. Okay, let's take a 10-minute break. Yeah. Okay, let's start again. The remaining part of this lecture will talk about binary search trees. I think they are much more fun than hashing. Hashing is just quick and dirty, but binary search trees are elegant in some way, I would say. Here we have a binary search tree where I have added a number of integers. 4, 2, 6, 1, 3, 5, 9, 7. This is called a binary search tree. It is a tree. The root is in the top, and it grows downwards. Topmost node, 4 in this case, is called the root of the tree. Binary tree means a maximum of 2 children for each node. So 6 here can have a maximum of 2 children. The left child of 6 is 5, and the right child of 6 is 9. So we are talking about parent node and children node, and each node can have a maximum of 2 children. That makes it a binary tree. Binary search tree means that they are ordered in some way. The left child is always smaller than the right child. So if you take a look here, the left child is always smaller than the right child. Smaller, larger than this one. When you're adding a new number, we would like to add 7. We should always start in the root. And we should compare it with the root. If it's the same as the root, well, then we have a duplicate element, then we stop. If it's larger than this one, then we go right. And in this case, if it's larger than 6, then we go right. If it's smaller than 9, then we go left. If it's smaller than 7, then we go left. It should be added as the left child of 8. number 7. Where should I add 10? Right child of 9. Just remember that the rules are very simple and we are repeating the same rules in every node. We start in the root and then compare it with the root. If the one that's to be added is larger, then we go right and repeat the same process. If it's smaller, then we go left. Yeah? So, if I would like to implement a binary search tree, this is a fraction or a fragment of my binary search tree implementation here. We have, similar to the linked list, we have an outer class, in this case called int BST, with an inner class. These are the nodes. They are just called BST. The user is interacting with an outer class int BST. If, for example, I would like to add an int here, then I check if root is null, that means an empty tree. Then I'm just connecting, saying that, okay, let's create a new node and attach it to the root. Otherwise, I delegate the question to the root. In the linked list, it was inside these methods that most of the functionality could be found. We were traversing the different, the sequence of elements, and then we were doing something. In a binary search tree, most of the complexity is down here. For example, I should show it later on. Each node contains a value and a left child and a right child. And each child is a BST again. So in the linked list, each node had the next element, another node. You can think of it here as if we have two nexts, one called left and one called right. Okay. This is the BST class, that means the inner class. We have a value, and initially they are null, both the left and right, and then I would like to add a new element to this node. If this, the element I would like to add is smaller than the value, and the left child is null, then I attach a new node. That was, I was reaching the end here, and I would like to go further down here, but I couldn't find a new node. Then I'm creating a new node and attach it there. Otherwise, the value I would like to add is smaller than the current value. I'm just asking my left child, add it to yourself. So then the add method in one node is calling the add method in the left child node here. If the value is larger, if the input n is larger than the value, we check, if we don't have any right child, we create a new right child. Otherwise, we are asking the right child, add value to yourself. You understand how it works? It's a recursion. We are simply describing the rules for what will happen in each node. And the rules are simple. If it is smaller than the value in the node, go left. If it's larger, go right. That's the basic rule. And if you can't find a node to add, then you add a new node. Otherwise, you delegate the question to the right child. I would like you to sketch the resulting binary search trees after having added these values in this order. I can give you a hint. The first value is always the root. But then add them in this 22, 19, 41, 52, and so forth. What will the corresponding search tree, binary search tree, look like in this case? Remember, always for every new element to add, start in the root and go left and right depending on the size. I give you a hint here. Where should the 41 be added? Yeah, I start over here. It's larger than 22, and I cannot find anyone here. Then I had to add it here. Where should 52 be added? Right child of 41. Yeah, we start over here. Is it larger? Yes. Is it larger? Yes. We can't find it. 52. 37. Left.
Right of 19.
Left, right. Start over here. Larger, yes. Smaller, yes. 16. Smaller, smaller. It's not that difficult. Okay, empty. Where should we add 12?
Left of 16.
Left child of 16 is the correct way to say it. 14. Right child of 14. Smaller, 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 larger. Don't try to add it right there. Always start from the root, and then it's very simple. So 32 should be added.
Left child of 37.
Very good. Do you want to practice one more time, or do you think you have got the idea now? Of course, I made an error. I made this figure, I think it was 3 years ago, and every year I remind myself that I should fix it. But we have an error here. What is the error? The right child is always larger than the parent. And here it's an error. It should be the right child should always be larger than the parent node. So here I added it in a wrong way. What will happen if I have them sorted? I start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What will the tree look like in that case? Yeah, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not good at all. Then we have a linked list in that purpose. So binary search trees comes with certain flaws. I will discuss them. Yeah. So in general, same elements added in different order, we get 2 different trees. If I take the same elements here, I think these are the same elements. Depending on in which way I'm adding them, the tree will look slightly different. How do I find them? Could you give me the basic idea for looking up whether 72 is in the tree or not? The same way as I'm adding them. I start in the root node. I would like to find 72. I start over here. It's larger than this one. It's larger than this one. It's larger than this one. It's empty spot. It's not in the list. So binary looking up things and adding things are basically following the same approach. The only difference is that we are return false if we find an empty slot, and we are adding a new node in the case when we are adding things. So contains method, that means recursive lookup. If it is less than the current value, then we go left. If left is null, then we return false, saying we haven't found the element. Otherwise, we ask the left child, do you contain this one? Go right. If it's not in the right, if we can't find it, then we return false. Otherwise, we ask the right child, look for n. And if it's neither smaller than or larger than, then we have found it. So we can immediately return true in this case. Any problems with finding it? Binary search trees, looking for something. So if I would like to find 14 in this one, I start over here. Is it smaller or larger? 14 is smaller. I go over here, I go over here, I go over here, and I find it in 4 steps in this case. Look for 34 over here. I go here, here, and then after 3 steps, I realize that it's not in the list. In general, this is very similar to binary search. Assume that we have a balanced tree. That means it was a nice looking uniform tree that looked like a triangle. In each step, I decide to go left. That means I remove one half of the element. So we are halving the search in each step. So it is the same time complexity as binary search. That means we will end up in logarithmic time complexity. Is this faster or slower than hashing? Slower. Logarithmic is slower than constant, but still much faster than linear time complexity. Okay, now we have a tricky one. Find insertion order for 1, 2, 3, 4, 5, 6, 7 that on average gives the fastest search and the slowest search. Yeah. A balanced tree. They look like this. We have filled all the levels. Then we have a balanced tree. If it starts to have a long branch over here, it is not balanced anymore. And a balanced tree is the one with the lowest depth. And the one with the lowest depth gives the fastest search. Yeah. So in what order should I add these elements to get a balanced tree? If I'm adding them in this way, then we agreed that it will be a one long branch. This will give the slowest lookup on average. The fastest one, we should produce something that looks like this. Where do we start? 4. Then 2. Are you sure? Okay.
1, 3, 5, 7.
It will give a search tree that looks like 4, 2, 6, 1, 3, 5, and 7. Yeah, it will give a balanced tree. Did you understand this one? What flexibility do I have? Do I have any option but starting with 4? No, I must start with 4 in order to get 2 equal sized sub-trees down here. 2 and 6 can be switched, and all these 4 can be switched. So the drawback with binary search trees is that we need to insert them in some kind of random order in order to get a balanced tree. We like balanced trees, and if we are inserting them in sorted order, then we will basically have something that looks like a linked list, and all the advantages with speed is lost. So in order for them to be functional and speedy, we need a balanced tree, which in most cases need a basically random insertion order. Then it has best properties. However, if you take a look at the Java implementation, they are using an implementation technique called red and black trees. These trees, you're adding them like we've done before, but once in a while they stop and reconfigure themselves to make sure that they are always balanced. We will not use it in this course, but when you're using the tree set in Java, don't worry about getting one long branch. The implementation will take care of it and make sure that you always have something which looks like a balanced tree. And you always will have a lookup, which is logarithmic in time complexity. Remove, a nightmare, dropped. Take a look in the book, I think they are presenting it. But removing an element and maintaining these properties of left child smaller is in general rather tricky. This is just the start of the code. it is much more complicated. Then we must introduce a method called delete mean here. Drop it, I will not present it. Just remember that adding things, looking up things, they are rather straightforward. Removing things, maintaining the properties of a binary search tree is tricky. Method print. Here I have a recursive method. This is the one that you should apply in each node, starting in the root node. Let's start over here, and you should apply this one. What will be printed? Sorted. Starting with 1. It will print 2, 1, 2, 3, 4, 5, 6, 8, and 9 in this case. These are tricky. It's recursion. But in general, it says go left. Go left as long as you can. When you can't go any further left and you're about, then we are printing this node. Then we try to go right as long as we can. We cannot go right. Then we are done up here. We return up here. We have been visiting the left part. We have done this part. Then we are printing 2, and then we go and visit 3 here. Yeah. So I think of it as we are doing, it says go left, do something, go right. You should read it like this. Go left, do something, and go right. Oops. We are doing a left traversal of the tree. Go left, do something, go right. It means we will go like this along the tree. And before we are visiting the right-hand child, we are doing something. In this case, we are printing it. So we will print it here, print it here, print it here. You understand it? Yeah. Just trying to take a look at an algorithm like this one and try to keep in mind what we are doing is tricky. The idea is that you should classify it as a left-to-right traversal or a right-to-left traversal. That means in which way we are traversing the tree. And you should also, visit left, do something, visit right. This is left to right, and since we are doing it in between our visit to left and right, we call it in order. Here we have an example of a right to left post order. We are visiting the right subtree, then visiting the left, and once we are done visiting in all the children, then we do something. If I should apply this one and print something here on this tree, we do a right to left traversal. That means we are traversing the tree like this. Yeah? And the final thing we do in post order is that before we are leaving the node at the end, we are printing its value. Then we would go here. We are not leaving. Here we are leaving 8. We will never return to 8. Then we print 8, print 9, print 5, print 6, print 3, print 1, print 2, print 4. Did you get the idea? So in order to understand algorithms traversing and doing something on a binary search tree, you should classify them. You should classify them as left to right. It determines in which order we are traversing the tree, and then whether we are doing something, the first thing we do in between the visits or after visits. We have left to right, right to left, traversal strategies, pre-order, in order, post order, when to do something. Okay, if I do a pre-order left to right printing. Pre-order left to right printing. What will be printed? Pre-order means at first entry to the node I print it. So I will start by printing 4, 2, 1, 3, 6, 5, 9, 8. No more printing. Yeah. This is a favorite question at the written exam. It's very simple for us to left to right in order printing of a given tree, and then we can just see its correct sequence, and we can correct it in 10 seconds, your exercise. Did you understand it? Any questions about this binary tree visiting strategies? Left to right means in which way we are traversing the tree. Pre-order, in order, post order, when we are doing something during this traversal of the tree. So binary search tree that are used in the tree set class in Java. Elements are placed in a special order. It means it's basically sorted. That means add, contains, remove very much looks like binary search, and we do it in logarithmic time. Most efficient if elements are added in random order, non-sorted, give a balanced tree with a low depth. Binary search trees is always sorted in principle. In order traversal, give a sorted printout. Okay, I showed you one algorithm, and after a bit of thinking, you said it will print them in sorted order 1, 2, 3, 4, 5. If I would like to print them in reverse sorted order, starting with the highest, could you just describe the traversal strategy that will be used? Right to left in order. Yeah. It will give you them in opposite sorted order. So they are in principle always sorted, easy to find the minimum and maximum value. What would an algorithm be to find the maximum value? Go right, go right, go right, until you can go no further, and pick the last one. You will find the largest element, and the smallest go left. So this class, Java util tree set, it implements the sorted set interface, and it's using this approach. The only thing that differs is you don't have to worry about adding them in random order. It will keep the tree balanced automatically. But it will have the same properties. You are adding a number of elements to a tree set in random order. You are iterating over it. You will get them in lowest first or highest first. You will get them in sorted order. Hashing was the alternative approach. Must provide an even distribution of elements over the buckets. Faster than binary search trees on add, contains, and remove. No ordering among the elements, printouts and iteration order in random in general. Min max means is a difficult question. Find the smallest element in a hash table. You have to traverse every linked list in the bucket, in every bucket to find it. So if speed is essential and sorting is not important, you should always use the hash set. If you are depending on being able to get them in sorted order or find the minimum or largest one, you should use a binary search tree. A final word about the third available set implementation in the Java library. It's called a linked hash set. It is basically a hash set. The only difference is that they are also maintaining a linked list. So the implementation, it looks like this. They have hash set and they have a linked list where they are storing the elements. When we are adding something, we try to add it to the set. And if it is true, that means not already added, then we are also adding it to the list. We are only adding it to the list if it's the first time we are adding it to the set. The ordering in this list will be used when we are iterating. It will then come out in what order? insertion order is it called. They are adding it to they are using the hash set for everything that requires speed, but every time they are adding it to the hash set, they are also adding it to the linked list in the order in which they were added for the first time to the set. So this one is something in between. It has you can predict what will come out when you're iterating over it. It will come out in insertion order. The first order it was inserted. When we are looking up, we are only using the hash set, and when we are removing things, we must remove them. So it is basically as fast as the hash set, but it contains this one as a backup strategy for maintaining a certain order. What is the drawback? Yeah, we are storing our element in two different data structures. Actually, it takes twice as much space as each one of them. So it comes with a penalty when it comes to memory consumption. But this one is not as frequently used. But the hashes, the tree set and the hash set, I'm using them all the time, especially the hash set. If I want to have quick access to look up, have I seen this element before, or something like this, I'm always using the hash set. It's very quick. The point class, I've shown you this example earlier on. A point is just one x, y point, both integers, that means a point in the coordinate system. Here I would like to make it suitable for both hashing and sorting. If I would like it, I would like to add a point to both a hash set and a binary search tree. Then I must implement comparable, and I must implement equals, and I must implement hash code. This one is used in the binary search tree to decide whether to go left and right. We must be able to compare two elements. That's why we're implementing comparable. These two were used for the hashing. I'm computing a hash code, and I'm comparing if they are equal. And they are equal if they have the same x and y value. What is this strange operator? Bitwise. It's working on bit level. So if I have one, it compares this one and do, what was it? XOR, exclusive OR. If both of them are 1 or 0, it will be 0. If one of them is, it will be 1. So it's just a simple way to take two integers and make a new integer. And these bitwise operators are very quick computational value efficiently. So I have my points implemented in this way. I have my program here. I have three different versions of it. One where I'm adding it to a hash set, adding it to a tree set, and a linked hash set. So I'm using all available set implementations in the Java library. This time I'm using the tree set. I'm starting by adding 5 points. I add the duplicates here, already available, and then do the thing. But later on, I'm printing them down here. I'm adding them in some random order here, but when I'm using the tree set, they will come out sorted. I said that in order to compare two points, 2, 7, 1, 9. This one is smaller since we start by comparing the x coordinate, and only if they are equal we are comparing the y coordinate. So I add them to the tree set in random order, but when I pick them out, here they come out sorted. When I'm using the linked hash set, I'm adding them, and they are coming out in exactly the same order as I was adding them here. So the linked hash set maintains the insertion order and disregards any duplicates. Hash set here, try it at home, do something similar. You will see that it come out random, and if you are running the program many times, it comes out in a different order. It's unpredictable how it behaves. Do you understand the difference between them? Do you understand that they are much faster than a list? In a list, if I have 1 million element and I would like to see, do I have element 643 in it, I must go through the entire list to find out whether it's there or not. In hash set, if everything works, I do 3 different computations and I'm already there. I can say, no, it's not here. So looking up is much, much faster for hash set, and also much faster for tree set. A few words about the map. What is a map? A map is another data structure. Set is one data structure and map is another data structure. A map, you are adding pairs. I'm adding 1 and Jonas, 8 and Jesper, 64. So we are not adding an element at a time, we are adding a pair to it. It's called the key and the value. And then it's designed for looking up. Give me the corresponding value for 8. It will give Jesper. Give me the corresponding value for 4, and it will give Johan in this case. So you're adding pair to it and you're looking it up later on. This one is called the key and this one is called the value. It is designed to be, you should look up on the key and it should return the value. So put means insert a pair, get means get me the value for the for this particular key. They are implemented in exactly the same way. We have a tree map and we have a hash map. They are using the same implementation strategies. Put 8 Johanna replaces Jesper as value for 8. So if you're adding a new pair with the same key, it will replace the old one. Can you come up with any situation where you can use a map? Well, a telephone dictionary. You would like to find the telephone number for all of you. Then your name would be the key value and the telephone number is the one we are looking up. So they are quite frequently used, the map. You would like to look up information related to something.
If I want to look up the phone numbers for everybody here, isn't the course number the one I should search for?
But just the telephone number, we have a list of names with a corresponding telephone number. And I would like to have this, implement this information in such a way that I can quickly find the telephone number for a certain person. Then a map would be a... No, just look up things. So the 2 key operations are put, a key and a value, and get. That means get the value for a corresponding key. They are generic. That means you must provide, didn't I have it up here? Yeah. I'm creating a new hash map here saying that it contains an integer as the key value and a string as the second one. So it's generic, but you must provide 2 types here, deciding what is your key and what is your value. And then it comes. You can ask, do you contain this particular key or do you contain this particular value? Is empty, and things we can expect from a map. And there are 3 versions of them. They are basically using exactly the same implementation as the corresponding set classes. So we have a hash map, tree map, and a linked hash map. About assignment 3, have you started on this part? We want you, these exercises are related. So in assignment 3, exercises 3 to 7 are related. Basically, we would like you to count the number of different words in a text file. You should read the text and you should identify the different words. And then you should add them to a set. And the set will recognize that, well, I've seen this word before. So it will throw away duplicate elements. So you read the text, pick out all the words, add them to a set, and then afterwards you ask the set, what is your size? And it will give the result will be the number of different words used in this particular text. We want you to do it first using the available data structures, hash set and tree set, and then we would like you to implement your own hash string and tree in this case, specialized for the class word. Follow the instructions. Just remember that you should get the same result, whatever set you are using. Of course, the number of words, different words, should be the same in all cases. Also, have you seen that we have published a competition? This is a VG exercise only for the one that thinks programming is fun. We have specified an interface, and now we are talking about mathematical sets with operations like union, intersection, and difference. Do you know about these operations? I don't trust your gymnasium. When I was a kid, we learned it as an 805, I would say. No. Assume that we have a set 1, 3, 9, 7. We have another set. B is 2, 3, 9, 12. A union B is then what? It is all elements here and all elements here, but no duplicates. So it will be, well, 1, 2, 3, 7, 9, 12. Not necessarily sorted as I did them here. What is this operator called? Intersection, and how it is defined? What? Elements found in both elements, in both lists. So it is only these two elements. So the intersection would be 3 and 9. And then we have set difference. You take the elements here and you remove elements that can also be found in here. So it will be 1 and 7. Did you get this one? This is the starting point, and then you take a look at B here, and if you find the similar elements here, then you're removing them from this one. So it will always be smaller than this one, or the same size. Yeah. So this is another data structure. We are providing an interface for it. We are also providing a JUnit test case to check the correctness of your math implementation. So all you have to do is to implement this one. You give it to the JUnit test, and it will say yes or no. Once you have made a correct implementation, you go to the benchmarking program that executes and measures the time for a large number of math set computations. It will do 1 million of these operations, 1 million of these, and 1 million of these, and a few other things. And it will measure the time and said, for your poor implementation, it took 3 minutes. Then you go back and think, I must do it faster than this. And then you improve your implementation, go through this step, and hopefully you can do it in less than 10 seconds in the end. The teaching assistants will also participate. They have promised to participate, so of course you should try to beat them. But they are quite good, so it will take you a bit of time. Do you understand the basic idea? So implement a fast and correct math set computation. It must pass the JUnit test, otherwise you're disqualified for the computation. Fastest implementation to benchmark is the winner. We would like to present some intermediate results. So if you have something that you think is good enough, send it to us. We will run it on my computer, I guess, and we will publish that. The fastest so far is Janti. He did it in 6 minutes. Very beatable, but so go home, and it is a VG exercise. Complete assignment 3 first, and then start to look at this one. See you next week. Bye. Ja, vänta. Or do you want it recorded?